replacing something called the natural base, which we're going to use this to replace the base in our exponential function. So normally, yesterday and on Monday, we talked about a times b to the x, where b was our base. So now we're going to be replacing our base b with e. It's the natural base. Now, here's what you're doing on that little yellow table. You are finding the value of e. E is a number. What other number do you know that's named by a letter? Like if I said this letter, everybody would know what number I was talking about. Pi is a Greek letter.
Oh.
Right? But pi is not, when you see pi, pi is a Greek letter. But when I say pi to you in math class, everybody thinks 3.14. So you know it as a number. So E is now going to be that for us in chapter 6. When I say E, everybody will think about the number E, whatever that may be.
So E is a number.
E is a number.
What is the number?
Well, so let me talk real quickly before you get into all the calculations. Yesterday we talked about this compound interest formula over here on the sideboard, right? Okay. What the yellow sheet is asking you to do over at the top of the right column, it says let P equal 1, let R equal 1, and let N equal 1. So we're like simplifying this whole compound interest formula so that we can really focus on what does N do. Okay. So notice that if I let all of those things equal 1, I get what's at the top of this column. 1 plus 1 over N raised to the N. Okay. Now, N yesterday represented how many times we compounded our interest, right? And I gave you some examples where we compounded annually, quarterly, daily, monthly, and we see some of those things in this column. So you're going to take your calculators and you're going to plug these numbers in for N and evaluate what you get out. Please don't round on these. They're going to be long decimals. Write out all the decimals. Okay, so go for it. You can talk with your pods. We're going to see what raising the value of N does.
Raising K's. Q.
What did you guys get for the first one? 2. Excellent. 1 plus 1 raised to N is 2. Or raised to first. Good. It's 2. When you guys have an answer for 12, will you
How's
write
that?
down the answer?
Because it's pretty much just 1 plus 1 to the first.
Oh, I didn't.
Whole decimal. Around here. When you guys have an answer for 355.
So I get
Can I see your calculator? Well, it's not 366. It's 1 plus 1 over 355.
Oh, 1
plus 1 over 355.
he says he didn't trust.
We gotta write the whole thing out.
When you guys get 8,000. And when this group gets 525,600, we put it on the board. And I'm going to have you guys do 1 million on the board. Okay?
Alright.
Oh, and I'm going to be great in here.
No. Which one? Seem right.
Yeah.
That is right.
Wait, that one doesn't seem right.
Okay, that's what I thought.
So maybe redo that one. Did you guys send the people with the nicest penmanship up to the board?
No, because I'm coming up here.
Oh yeah, Josh is on it. No, it's fine.
Oh, there it goes.
My bad.
His might be the most beautiful of all.
And then we have.
TJ, which one did you write?
12.
That's not even bad.
I wrote 12.
It's no, it's not bad at all.
I don't have great handwriting.
Okay, excellent. Okay, so you can kind of take a peek up at the top and see if your decimals are agreeing with ours. But what we should be noticing here is like we are really increasing the value of n, right? Like big. And as we get bigger and bigger and bigger, we're noticing less and less change. Okay? Which makes sense based on what we've talked about with exponential functions. Okay? But we started off low at 2, and then we go 2.613, 2.714, 2.718. I'm seeing change. But after 8,760, it takes me more than 4 places after the decimal to even notice a change there. So what we say is that as n approaches infinity, this value, you know, and like n approaching infinity would mean like do a billion, do a trillion, right? Keep going bigger and bigger. As n approaches infinity, it gets closer and closer to the value e. And so we're going to say that number is e.
What?
1 plus 1 over n raised to the n as n approaches infinity is the number e. Which e is about what? Like when we do pi, even though there's infinitely many digits, you say 3.14. What could we say about e? E is 2.718 is what we usually say for e.
Oh. So pi is a word? I mean a number?
Yes.
Why is it work?
Well, dur.
I thought I was going to say something.
So I'll say this. E is approximately 2.718. You know, like after the third number, after the decimal, getting into the 10,000ths place, that's going to make less change. So we'll go out 3.
Is E always almost or about that? Or
Yes.
Is it, okay, no matter what the numbers are?
Well, E will be as n approaches, and E's like the concept of E is as n approaches infinity. But can we ever get to infinity?
No.
No. So we can never really say what E actually is because there is no n number. But we're just saying that as E gets bigger and bigger, see how like these last 3, I went from 9,000 to 500,000 to 1,000,000 and nothing changed. I mean, yes, things changed, but 2.718 was the same.
I mean,
So like as it gets bigger and bigger, it's 2.718 other stuff.
I mean, like in the formula, like since we set all this stuff to equal to 1, if we change those numbers, does E change, or is that not?
No, E is that value.
No matter what.
Then the formula will change when you put other numbers in, of course, because you have different starting amount. But right now, with starting amount 1, E, we're just investigating how to find E. Okay. So E is the number 2.718. Now, let's all find E on our calculators.
Wait, it's 1?
EX. Or yours.
Is it E?
Okay, underneath the second button, if you go 2 down, there's a button that says LN. And above LN, it looks like E with a little exponent. Do you see that?
Mm-hmm.
Okay, so you have to do second LN, and then it will bring up something most of you will look like this, E to the something. And if you just want to see E, you'd have to raise it to the first, and it will give you this 2.7182818.
Wait, so will that repeat like the 1828? Was that repeated?
Well, it will start following that pattern, but remember, we can never stop it because we can always go more than we did before. So it just keeps going. So like the last numbers won't be 1828,
Right,
but that just keeps getting further and further in the back. Yeah.
So like with pi, it's like, isn't it over just what is pi? 3.14. So what's is there like an exact? For
Well,
E?
pi is not exactly 3.14.
Right. That's
we
why
just
I'm
use
saying
that.
E is not-
2.718.
But pi never varies, right?
E doesn't either.
It doesn't.
2.718. Okay, E is the thing at the top of the column. 1 plus 1 over n raised to the n.
Okay.
Let P equal 1, let R equal 1, let T equal 1, and only change n. As n increases towards infinity, that gives us the value of E. E is always 2.718. We just found it. It doesn't matter if I put 1 trillion in there. I'm still going to get something that looks like 2.718. It's never going to change again. The first 3 digits after the decimal. Everything else is changing behind it, right? But it's never going to change again. So we've just decided it's 2.718. Okay, that means E is considered an irrational number. It can't be written as a fraction. Well, it's as n approaches infinity, so it just keeps going. Okay, so we say that E is irrational. As a side note, if you're interested in the number E, you can go online and Google some things and find some interesting things. I'll just show you real quickly. You don't need to know this for any reason, but just to kind of bring in our previous chapter 10 when we did probability, another way to find the value of E is to use factorials. So E is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus ... If you spend some time typing into your calculator, you would get something that approaches E. So there's different ways to estimate E, but what you need to know going forward is just that E is 2.718, and you all know how to find E in your calculators. So you're going to use the E button. Just like when you were doing geometry, didn't you hit pi button instead of 3.14? Okay, so if your calculator has an E button, you're going to use that instead. Did everybody find E? Check on yours. Liam, do you have to do second PRB? Does it say log? Do second PRB. And then it'll take you to the, now you need to scroll over to LN and then choose E. Okay, now I want to go back just really quickly to this table and talk more about why it's called the natural base. Okay, why is it called the natural base E? The reason why we want to know about E and this thing about n going to infinity is, like this compound interest formula we talked about yesterday, this is on a schedule, right? Like I put money in the bank and the bank says, I'll give you a fraction of your interest every 3 months, 4 times a year. Or I'll give you a fraction of your money every day, right? I'll give you a little bit. It's on a schedule. And they'll put a little bit of money in my account and then I'll earn interest on interest. But the exponential function can model things in the real world really well, like I was talking about the spread of disease, right? But these things don't always run on schedules. So we need to know how to represent that growth or decay if it's doing it all the time. So let me give you some examples of good examples of when things are growing in nature. You are what? 15?
Growing.
Yeah, you are growing, exactly. That's my point. You are 15, 16, something like that. Okay, 14.
14.
You grow all the time. Right now, you are actively growing. It is not like on your 15th birthday, you wake up and you're like, oh, I'm 3 inches taller and all these things have changed about me. You have changed over the course of the whole year, right? That would be so weird.
That would be creepy.
If you grew on a schedule. People aren't the only things that grow like that. nature grows like that, right? Like animals or trees. Like a tree doesn't just sprout branches on the first day of the month, and that's the only time it gets a new branch, right? It's like constantly growing on itself. So how do we show this thing where like we're growing all the time? I also always talk about like your cells dividing. Like right now, some of your cells are dividing. It's not like your cells, yeah, isn't that weird? Can you feel it? Okay. It's not like your cells work on a schedule and it's like every morning, 7 a.m., my cells divide and mitosis happens and this and that, right? It's just happening all the time. So we want to show that, like as n approaches infinity at the bottom of this slide, some of you might recognize these numbers. 8,760, 525,600. Anybody recognize those? Yeah, that's how many minutes there are in a year.
Oh, really?
Good job, Sierra.
525,000.
Seconds.
Yeah, it's the song from Rent. Okay, so I stole my numbers from Rent. Okay, but now 1 million. But like, these are just saying like, instead of compounding every month, let me compound every day, let me compound every hour, let me compound every minute, let me compound every nanosecond. At some point, it doesn't matter how much faster I compound. It's just getting closer and closer to this 2.718. So that's what we mean when we say natural base. I always tell people, think about nature. It's just what's happening in nature. Okay, so let's do some examples like you're going to do on your homework tonight. Natural base exponential functions can be written as y equals a times e to the rx. So these are functions we want to show modeling things where they're like continuously growing. They're growing all the time. There's not a schedule. I couldn't tell you how many times it compounds per year because it's just always compounding. A will still be our initial amount. E is replacing our base, right? That's why we're calling it the natural base. And then notice that in your exponent, this is where you could put your rate. Now that could be a rate of increase or decrease. It just depends on the context of the problem. If something is continuously increasing or continuously decreasing. Also, like, I think you'll probably get some problems at some point about like carbon dating from science class. The amount of carbon left in a substance will help you date how far back it went. That would be exponential decay. If r is greater than 0, you're going to have exponential growth. If r is less than 0, it's going to represent exponential decay. Because what happens when r is less than 0? You're going to have a negative exponent. If e is raised to a negative exponent, so let's say e to the negative 1, for example, that's really 1 over e to the first, right? And 1 divided by 2.718 is something that's less than 1. Okay, so anytime you put a negative up in r, you're going to get exponential decay. Now, in order for you to do like we did on Monday, which is graphing exponential growth and decay with the natural base, you're going to need a calculator. So these, on Monday we did it just by hand, figuring it out ourselves, flipping the base, etc. Since we're using E, you're going to use a calculator. We'll do the one on the left. I think 1 will be sufficient, one graph. Y equals 2.5 times e to the x. Let's graph that one. Is that exponential growth or decay? It's growth because the exponent is positive. What must have been my rate?
1.
It must have been 1 because it would be e to the rx. So I must have a rate of 1 up there. Okay, but you don't really have to worry too much about that. You're just going to be calculating. So in order to get a graph, I probably need a few points to plot, right? What do you want to put in your table of values?
0.
1.
Negative 1.
Oh, negative
Yeah, I usually try to do some positives, some negatives, but you could add 2 here if you wanted. Okay, and now just type them in your calculator. Right? Get some values. So you could type in your calculator 2.5 and then get your second natural log for your e and then raise it to the -1. That's all you have to do.
Can we round these ones?
Yeah, I round because you're gonna graph it, so like you don't have to go 10 decimals out because you're not gonna graph that. So I'd say like what, 0.9?
Yeah.
For the first one. What's gonna happen when you put 0 in? 2.5 because e to the 0 is 1. And then I'd probably go back to my calculator at this point. 2.5 times e. It's 6.8. 18.5. If anybody's having trouble calculating with e, let me know. We just want to make sure that you can use your calculator. I've got points, so I can plot them. If you're unsure of what your graph looks like, plot more points, right? Choose some other values. I would say this is probably enough. So what? -1.9, 0, 2.5, and 1, 6.8. And then like 2, 18. That's too far, so I'm not going to graph it. And you can imagine what's going to happen on the other side. Going to be like our asymptote, right? We're never going to get to 0. So something like this. This is still exponential, so the rule of the asymptote still follows through. If you put in bigger and bigger negative numbers up there, well, you still get something really small, but more than 0. Does anybody have any questions about that graph, like how I got it? It's really just calculation to me. Yes? Oh, yeah. And then did you do times 2.5? That would work. So like I saw in your work you had like an e to the first. And then you just need to multiply it by 2.5. But the other thing you can do, which I think I would probably do, is just 2.5 e to the first. Like you don't really need to separate it. Okay, now it does ask you to do domain, range, and asymptote. So what do you say for domain?
All round numbers.
Yeah. What do you say for range? Y is greater than 0. And asymptote? Awesome. Okay, so far those things haven't really changed for us. And this one is exponential growth. So notice, like as you're moving to the right, your like rise over run steps are getting bigger and bigger. And this one over here would be exponential decay. So as we come to the right, the steps will get smaller and smaller. It'll approach the asymptote. Okay, we got to talk about continuously compounded interest. So remember yesterday I gave you this compound interest formula, and I would say your interest is compounded monthly, daily, quarterly. So you could say, and it's 12, and it's 365, and it's 4. If I tell you that your interest is compounded continuously, it's nonstop, it's all the time, can you give me a number for that?
No.
No, it's basically what happens when n approaches infinity, so we're going to use the number e. So this formula looks like A equals P times E to the R times T. It's basically that same formula that we just graphed, the initial amount times E to the RX. So P is principal, A is balance, R is rate, interest rate, and T is time. Only use the PERT formula when it says compounded continuously. Back in my day when I was in high school, the shampoo PERT Plus was really popular. And so we called it the shampoo formula. But PERT Plus is not as popular anymore. So we just call it PERT. Yeah, I know. So weird. Okay. Let's look at an example. It's really not too terrible. It's one of those, like, once you know the formula, plug and chug. We're going to deposit $10,000. Annual interest rate is going to be 4.5%. And we're going to find the balance after 8 years. And again, you'll just have to pay attention to directions. What does it say about compounding?
Monthly and continuously.
If it says monthly, then I'm going to use my old formula. N equals
P1 plus R.
12. Yeah. Amount equals $10,000. You practice this on your homework. Times 1 plus 0.045. Don't forget to change it to a decimal. Divided by 12. Raised to the 12 times 8, which is 96. Okay. So I'll get an answer there. Bless you. And then if it says compound continuously, do you know what N is? No. So I can't use this formula. I got to use PERT. So I say the amount in my account is my principal, $10,000, times E raised to my rate, 0.045 times 8. And then you're just plugging in your calculators and getting your two answers. I'll put up what my answers are so you can verify. I would definitely try your PERT formula here to make sure that you can do it. For the first one, compounding monthly, I get 14,323.65. And then for the PERT formula, I get 14,333.29. So it looks after 8 years. Going from compounding monthly to compounding all the time, I've only made $10 extra. So we can see, like, it's not really, like if a bank is running on a system and compounding every day or every month, it's not really cheating us out of that much money to not compound continuously. But you still should always make more money the higher the number of times the compound is. You have a homework assignment. There's a worksheet today.
I love this because you don't have to go back.
Big facts.
I hate drawing graphs. Yeah, and it takes like half an hour to do something to make anything. It took 5 minutes just to draw.
What time have you noticed this happening?
I just like drawing that.
I just hope.
Let me know if you had trouble with either of those financial formulas. I will assist you with your calculator.